Hi, and welcome back to the week 3 video number 1. We are still a little bit behind of where I want to be, but I figure I'm going to start naming these videos at the start of the week, so I don't want to start calling this one a week 2 video when it's already Sunday of week number 3. So here we are, week 3, video number 1. This is actually going to be a response to a question I received in email to clarify what I talked about in the last video. So this will be basically a clarification of what I talked about in week 2, video number 2, where we were looking at the actual executable file in our, oops, brought up the wrong one there, executable file in the bless editor, in the hex editor. We're seeing actual hex bytes of our first assembly program and just trying to understand a little bit about what's going on here. And some of these pieces are going to fill in more later. But most of the details of what this executable file looks like are not that important to you. So I don't want you to feel overwhelmed if you don't piece together what every number, every code in this file actually represents. But I do want to get you a better feel for what I was talking about last time, because you should have some sense of whether you're starting with something like a C program or an assembly language program. Once the compiler and linker do their thing, what do you really end up with, and what's really going on under the hood? That's kind of the ultimate goal of this course, is so that you have some understanding of what's going on under the hood, how these programs work behind the scenes, that even if you never go on to do assembly language programming yourself, or working in assembly language, you will at least have a better foundation to understand how computers work in general, which I believe will make you a better computer programmer, a better computer scientist, a better computer professional in general. That's one of the main reasons why this course is part of the curriculum. So let's go ahead and kind of dive back into it with the notes that I created for this video. So let me make sure I pop up the right things here, and let me zoom in a bit there. So there's 3 things I want you to make sure you understand clearly before we continue this discussion. One is offsets, the other is addresses, and the third is data. Okay? Now, all 3 of these things are things that we will very often look at in hexadecimal notation. Okay, we might also look at them as decimal numbers. It just kind of depends on the situation and how we are looking at these things. But especially offsets and addresses we will often look at in hexadecimal. Data, we probably kind of switch between looking at it as hexadecimal and looking at it as decimal, just kind of depending, again, on the situation. We're much more likely to switch off there. But at any rate, so what is an offset? An offset is a count of bytes from some starting point. That's really all it is. Or as I put here, a relative byte position from some starting point. I might as well say it the other way. A count of bytes from some starting point. So start counting at 0, okay? So hopefully 1 or 2 of these ways of saying it make perfect sense to you. And some examples, and most relevant to what we're looking at here is the byte position of something in our ELF format executable file. So offsets are important, and so understanding offsets, what you're looking at with an offset, is important. Addresses. Addresses are kind of like offsets, except it's specifically the address in the computer's memory. Okay? So when we're talking about addresses, I don't think we'll ever talk about addresses in any other way in this class other than a specific byte in computer memory. all the bytes in computer memory, I might as well add this to the notes, all the bytes of data in computer memory, and here we're talking, let's see, let me not go off too much on a tangent. So all the bytes of data in computer memory have an individual address, okay? In i386 architecture, so this is 32-bit architecture. What do we have? We have 2 to the power 32 possible addresses. Remember last time, actually maybe I'm clarifying video number 1? Which video did I need to look at which video I talked about what in. So okay, it was video 1 I actually talked about, we actually looked at the binary file. So and then video 2 I dove into the, learning some number systems in hexadecimal. So actually, I'm not clarifying week 2 video 2. This is more clarifying week 2 video 1. So basically kind of diving back into that a little bit and making sure that we clarify what we're talking about there. So let's go ahead but let's look at what we were talking about with binary numbers before. So number systems from week 2. And these clarifying questions, like how many different combinations of 4 bytes, or how many different combinations of 32 bits can you have? Well, that turns out to be 2 to the 32. As it happens on a 32-bit machine, you have 32 bits that you can use to represent an address of a byte in memory, okay? And we're not going to get into it in this video, but we're going to kind of look at how to think about computer memory and so forth. But for now, just think of computer memory is just a huge array of bytes, okay? So if we come back to what we're talking about now, computer memory, that's just a huge array of bytes, okay? Now, we say possible addresses because your computer might not have the full 4 gigabytes. So what is, first of all, what is 2 to the power 32? Well, that turns out, whoops. That equals, if we put it in notation of gig, so 2 to the 32 bytes, that's actually about 4 billion bytes. It's a little bit more than 4 billion, but it's about 4 billion bytes. So that's 4 gigabytes, or 4 GB. All right, so your typical i386 architecture has a maximum memory capacity of 4 GB. There might be, depending on your operating system, there might be tricks that let you have larger memory, but then it would only use 4 at a time. At most, any process running would only have access to 4. And you could have less than 4 gigabytes. So while we have 2 to the 32 possible addresses, the real memory may not have that many bytes, or might have more, and the OS does some juggling, shall we say. So just kind of keep that in mind, though. With standard 386 architecture, 32-bit architecture, we're dealing with an address space. That's another word for it. We call the range of possible addresses an address space. Okay? So the address space is 4 gigabytes, but we may not actually have that much to work with, or we may actually have more than that to work with, but we only work with 4 gigabytes at a time. And when we talk about addresses, we're talking about a specific number assigned to a specific byte in memory. That's it in a nutshell, except that I have these 2 asterisks here because, in a way, what I just told you isn't true. When your process runs, don't need that. When your process runs, what it sees, what your program sees, is 4 gigabytes of memory available out there that it can address. But that memory is already being what we call virtualized. This has nothing to do with your virtual machine. This is something that the 386 processor does for you, and it's between the processor and the operating system work together to manage the memory. So your process, your program that you might build with a C program or with an assembler, or with a C compiler or an assembler, your program will think that there are 4 gigabytes of memory out there and it can use whatever addresses and so forth. But the reality is the addresses used by your program get remapped to other real addresses. But that's all kind of handled behind the scenes. We may not be able to touch on that significantly at all in this class of what really happens. We may look at it a little bit, but for now, just realize that, strictly speaking, when we talk about addresses, we're already talking about a kind of virtual address to a virtual memory space, and the physical address might be something completely different. But for now, we are pretending that these are physical addresses, and we're not worried about this extra level of virtualization that goes on. So there's offsets, which are always relative to some starting point. There are addresses, which refer to specific addresses in memory. And then finally we have data. Data is the actual data that appears in a file or appears in memory. So whatever value particular bytes in a file or particular bytes in memory have, that's data. So I just want to make sure you, first of all, distinguish these 3 concepts. A relative byte position, a absolute address in memory, or the actual data that is stored in a particular byte in a file or in memory. Okay. Let's see. I would say I'm going to rephrase my notes here. The actual content of bytes in a file or in memory. There we go. And when we talk about data, keep in mind that even machine language instructions are data. Okay? So let's keep those 3 distinctions in mind, then let's move on. So to kind of what I was showing you before. So let me bring up, first of all, the Wikipedia page again for the ELF format. And we zeroed in on a particular field out of the header. So we wanted to look at this field from the header. So this field is at offset 0x18. So that's offset 18 in hexadecimal. So that's actually 16 plus 8. That's byte position 24. Okay, so that's 24 bytes into the file is where we're looking. And we're in the 32-bit architecture here. Okay, so when you're looking at this table, what we're interested in is the 32 bits. So when we come down here, this is a 4-byte data item starting at this byte position. So the byte position in hexadecimal is 18. In decimal, that's 24 bytes into the file. Okay? So back to the notes briefly. So starting at offset 0x18, or 24. You know, that's basically just 16 plus 8 equals 24 bytes into the file. Okay. So at that position, there are 4 bytes which give the address where the first instruction will be stored in memory when the file is loaded by the operating system. Okay? So when your actual executable file gets loaded into memory, we know what the address of the first instruction is going to be when it gets into memory. So let's look at that. Come back over here, and now let's look at our bless file, and let's find byte position hex 18. That should be right. No, that's 1E. 1918. So that's this byte position, and we want these 4 bytes. Okay. Now, these 4 bytes are 80, 80, 04, 08. So I'm actually going to add that into the notes now. Oops. 80, 80, 04, 08. This gives us address 08, 04, 08. I'm sorry, 8080. Okay. And let me just say Y reversed. And because of little endian byte order, so just get this little endian thing in your head. Whenever you use more than 1 byte to represent a number in 386 architecture, the bytes are in reversed order. Okay? Not the bits. The bits within the bytes are in normal order, but the bytes are in reverse order. And actually, let me go ahead and add this kind of as a third thing. Be sure you understand this. So I'm going to make kind of a section on this for its own sake. And whoops. Here's what I can do is fix that. Okay, when representing integers. All right, so this is specifically applied to integers. Why? Okay. There we go. When representing integers in i386 machines and many other computer architectures, we need to know what order the bytes come in. So, little endian means the order of bytes is high address to low address. Okay. Now it's important. The order of bits within the bytes is normal. Okay. And another thing we should say, when representing integers in i386 machines, let me add something here. Let's say in memory or in binary files. Okay. So that's what that explicitly this all applies to. So this is when we're talking about bytes in memory or in binary files, unless told otherwise, I should say. We for 386 architecture, we use the little endian byte order. Okay. Now, again, what does that mean? When we're representing integers, it means, and it's basically very specific to the representation of integers. It may also impact how floating point numbers are structured, but we're not going to look at floating point in a whole lot of detail in this class. But the integer representations, you really need to understand. So when representing integers in i386 machines, the order of the bytes is small to big, okay? And I'm going to clarify that a little bit more, but so we're in little endian. That means the order of the bytes is the high address to the low address, or we can say the small byte first, largest byte last. Now, the next thing we need to make sure, the order of bits within the bytes is normal, okay? And I want to make sure that you understand this does not apply to registers when we get to those. All right. The move and related commands in i386 assembly languages take care of the ordering for us. So most of the time, you don't have to think about it. Okay, but you should know it's there, and you should understand it when you are looking at particular things in data. Okay, and the fact that it does not apply to registers, that's something that might confuse you later on. It applies to memory or binary files. Okay, so when we're looking at integers represented in binary, if we're putting them in a file or putting them in a memory, we're probably talking about little endian byte order. If we're working on a Windows machine or on 386 architectures, or a Linux machine on 386 architectures, even Mac OS on 386 architectures, and so forth, any of these, we're almost always going to be using little endian. Now, there are computer systems that do the other, that use big endian, and that creates headaches in terms of transferring data between, and somewhere somebody forgets to take care of switching that format in terms of the byte order, and so completely changes the value of integers. So let's go back and look at our number systems notes briefly. Did I take any time specifically to talk about that? Trying to see. I think I talked about it in the video, but let's just look at an example. So yeah, so let's look at an example. And we'll actually take that example from, actually, I'll come to the example naturally as we start looking at this file. So let's look at the first assembly program ELF executable file again, and let's start now to understand things. So again, if we go back to the the wiki page. Let's see. I think I have it here. There we go. If we go back here, again, we said if we're looking at the header of the file header of the L file, that's just the first so many bytes. Let's see how big is the file header. We expect that to be in hex 32, so that's 3 times 16 plus 2. We expect the file header to be 50 bytes long. So let's go ahead and look at the file header back there in the hex editor. So let's find everything up to OX32. So right there, everything I have highlighted here is the header, okay? That's the first 50 bytes of the file. Now, if we go to position OX18, okay, so that's actually 24 bytes into the file. So right now, OX32, that's the last byte. Actually, that's the first byte after the header. Right there, first byte after the header, last byte in the header. But let's jump to OX18. All right, so here's OX18. This byte right here, okay, that's highlighted with red. Now again, the bless editor is a little bit weird, and maybe the way I was explaining this before didn't make a lot of sense, so let me add that to the notes as well so you can read it as well as hear me say it. Whoops. So as far as there's the little endian order, and so another thing, the bless editor quirk. All right. And I want to make sure you understand what I'm talking about with this quirk. The quirk of the bless editor is that the Windows, I should say the information at the bottom interprets bytes starting at the cursor position, okay? This is strange when you select multiple bytes. Or actually, it doesn't even bytes. Typically, you wouldn't select just one byte, or even just one byte. Okay, if you drag right to left, the cursor will be at the first byte of your selection, okay? This will mean the info at the bottom will correspond to the selected bytes. All right. If you drag left to right, the cursor will be invisible. So you can't really see where the cursor is after you select text, but the cursor will be invisible and on the first byte after the selected text. This means the info at the bottom will be unrelated to the selected bytes. Okay? Want to make sure you understand that. If you don't understand that, pause, read it again until you understand. Then come over here to your virtual machine and select some things until you understand. So let me show you. For example, look at these 4 bytes right here. Well, there's a 1, a 0, a 0, a 0. Okay? Now, look down here in terms of how it is interpreting that for us. it says negative 128. Well, that might make sense somewhere. Well, actually, the best place to look is right here. This actually shows you, yeah, so let me flash the cursor on this multiple times. Look here, all right? That's actually showing the 4 bytes that are being interpreted everywhere else. So 8080080408. I'm sorry, 80800408. That's what is being, well, the 80, that's being interpreted here as, and here. These 2 bytes are being interpreted here and here for 16 bits. All the 32-bit stuff is interpreting these 4 bytes. But let's look up, where are those 4 bytes? Those are these 4 bytes that are not highlighted. You see that? They're not highlighted. And the reason is I dragged from left to right, okay? And that leaves the cursor blinking right there. But except the cursor is invisible now, so this is just a quirk of the Bless editor. Just don't let it throw you off, okay? But if you drag the opposite direction, it puts the cursor in the right spot. So let me drag this direction. Oops. Ah, it's a little bit sticky. There we go. So now we have 000000. I should say we have 01000000. Because I went from left to right, the cursor is now on this first byte. It's right there. Ah, there we go. All right, so now you see down here 01000000. So now we know that we're interpreting the correct 4 bytes. All right, so everything here, whether we look at those bytes as decimal numbers, as octal numbers, as binary bytes, signed 8-bit, signed unsigned 8-bit, signed 16-bit, unsigned 16-bit, etc. Now we are interpreting those bytes. We're interpreting the same bytes that we have highlighted. Okay, that's the issue with the Bless editor. So now, with that out of the way, let's go back to what we're looking at. Okay, so back to, again, let's look at the ELF file format here for a moment, if I can bring it up. So, ELF file format, we have the header, which is 50 bytes, and we are specifically interested in looking at the entry point of our program, which we see is mentioned at byte 18 hex, which is byte 24 if we interpret that as a decimal. So if we come back over and we find byte position 18, we end up here, but let me select that the other direction. There we go. All right, so 80800408. Those 4 bytes are the address Those 4 bytes are the address of the entry point or the first instruction of your program. That's where, once this gets loaded, once the program gets loaded into memory, boom, that's where it will jump to and start doing the actual instructions of the program. So that is now an address, okay? That's going to be the address in memory. So we see that that is 80800408. But what address is that really? Well, we have to remember little endian encoding, all right? So little endian encoding means that the byte order is, first it's 08, then it's 04, then it's 08, then it's 80. So we have 08, 04, 80, 80. Those, the bytes in that order give us a hexadecimal number for the address. So that's what the little endian business, oops, don't want to do that yet. I want to go back to our notes. So that's here. So using a little endian example in the file at position 0x18, we have 4 bytes representing the address of the entry point, the first instruction of the program. Okay, and at that point, we have those 4 bytes. So what are those 4 bytes? These 4 bytes. All right. Now that was 8080 04 08. Okay, and that's in hexadecimal. I'm just gonna say in hex. All right. Now, because of little endian, the integer represented, which is the address, is in hex. Well, I'm going to put the 0x in front of this time because I'm going to run them together. Now I have to take them in reverse order, so I have to go 08, 04, 80, 80. Okay, so double check me that these are in the reverse order of these. And once you've got that, then you've got it. That's a little endian. Okay, so from there, and if we want to see that in decimal, well, then you would have to take 0 times 16 to the power of, see, we have 0, 1, 2, 3, 4, 5, 6, 7. All right. Plus 8 times 16 to the power of 6, and plus and so forth. And I think a little copy and pasting here will save me some work. So then we have 16 to the 5. Lost my superscript. There we go. 5 and 4 and 3 and, oops, didn't type 3 when I meant to. 2 and 1 and 0. And now I have to get all these coefficients right. So that should be 0. That should be 8. That should be 0. That should be 8. And let's see. So I have 0, 8, 0, 4 here. And then I didn't get that exponent fixed. There we go. So let's see. 0, 8, 0, 4, 8, 0, 8, 0. So it looks like we've got it. And wonder. Oh, I'm gonna have to do a little quick calculation over here just to be complete. Make sure we have a complete example to look at. All right, so that actually turns out to be that number right there. And Just want the text. So there we go. All right, so and I'll just add decimal here. I guess I said in decimal at the beginning of that line, so hopefully that's perfectly clear. So that's how little endian works. So you look at, say you have 4 bytes in a file, you have to take this byte, then this byte, then this byte, then this byte if you want to interpret that as a 32-bit integer. If you only have a 16-bit integer, then you do the same thing, but it's just 2 bytes and so forth. And remember, the bits themselves inside the byte, never think about the bits being reversed. Only think about the bytes being reversed. And again, remember, this applies to bytes that you're looking at in memory or in binary files. It does not apply to registers. So when we start talking about registers in more detail, just keep in mind that you don't think about registers. There is no endianness for registers. Registers are just registers. They have all the bits and all the bytes in exactly the right order. They never get that confused. And the assembly commands that copy data to and from registers take care of the endianness for you. So usually when you're writing your assembly programs, you usually don't have to think about it. But if you're ever actually looking at binary data, if you're looking at the data in memory, or you're looking at the data printed in a data file in a hex editor or something, then you'll get thoroughly confused if you don't remember the endian ordering of your bytes. So be sure you remember endian ordering, okay? That's very important. It's going to cause you no end of headaches and waste you a lot of time if you get confused on a programming assignment later on in this class because you forgot about endianness. So remember endianness, okay? Make sure you understand it. Make up your own exercises, practice your own conversion back and forth, look at more of the numbers in the data file and make sure you understand what they are, that sort of thing. Okay? So, and make sure you understand that quirk with the bless editor so that if you are trying to look at data, you are looking at the interpretation of the data that you want, okay? That's the only reason I talk about that. It's almost maybe more confusing for me to tell you about it than to just let you kind of figure it out for yourself. But yeah, just keep in mind if you want to select 4 bytes to look at, do it right to left, and that way the cursor will be on the first byte of your selection, and you'll have the same bytes down here. And you can also just make sure, just look at what it shows down here in the hexadecimal window, okay? Because this window is not affected by endianness. It's not showing you that as a hexadecimal number, so endianness is not affecting it. And that's just showing you the 4 bytes you have selected, and or it's actually showing you the 4 bytes from where the cursor starts, okay? And here the cursor is at the beginning of my selection. If I select left to right, the cursor is on this 3-4, and so the endianness, or this has nothing to do with endianness, so the bytes it's showing me are these 4 bytes, and so all these numbers here are interpreted based on these 4 bytes here, okay? So, so just keep that in mind if you're trying to look at things in the bless editor. What is it showing you down here? It's the bytes starting wherever the cursor is, and you need to make sure you know where the cursor is. Okay, now, finally, we can kind of get, well, we are looking at it, what we wanted to look at. So we were looking at byte position 0x18, which has these 4 bytes, which because of little endianness gives us this address in hex. So this is all in hex. All right. So now this tells us something about where the program will be loaded in memory and where the first byte, the first instruction is going to appear in memory. All right. Now, where is that first instruction in the file? Well, that's a good question. The the first instruction in the file is actually going to appear at offset 80. Now, how do I know that? Well, there's a couple ways we can look at this to understand how to know that. So we're going to get a little deeper into the format. So let's come up here and look at the format overview, this diagram here. And what we'll notice is that at the bottom there is going to be this section header table. All right. Now, I'm not expecting you to parse everything out, but I just want to show you so that you kind of believe it and understand where things are and how things are related. So let's go down and look at what a section header looks like. There's actually going to be 6 sections. There's going to be the 2 that you're familiar with already, the .text and .data. There's 4 other sections it's going to create regardless, that you don't actually specify in your assembly language program. And each of these has a header of hex 28 bytes, so that's actually 40 bytes. 2 times 16 plus 8 is 40. So that's hex 28, 40 byte section headers. So groups of 40 bytes are what we want to look at here. And we can just do that since the section headers start from the end, or all at the end of file, we can just keep counting groups of 40 bytes back from the end of file. So let's do that. If we come here, just take my word for it, that's 40 bytes right there. The way I have things lined up, and I suggest if you're doing this yourself, change the width of your bless editor so that each offset here goes up by 32. Again, 32 in hexadecimal, 32 is a 2-0. So that's why we're seeing 2-0, 4-0, 6-0, 8-0. That's all going up by 32s in hexadecimal on these offsets. So 32 plus 8 is 40. So right from there to there, that's 40 bytes. Okay, so that's one section header. So from here to here is the next section header. From here, and then, whoops. That's the next section header. Back and working my way back more. Another section header, working my way back more. Looks like here is another section header right here. If I did that right, I hopefully didn't get off, but I think I'm looking in the right spot. This is the section header for the text section of the file, okay? And now let's go back to our executable file format. Why does it do that to me? Okay, there we go. Now let's go look at the format of a section header. If we look at the format of the section header, we've got different pieces of information. We can see these byte offsets of where that information is located. So if we come up here, I want to look at 2 things. Right here, the address and offset. Okay, this is going to be the address of that section in memory. All right, this is the offset of the same section in the executable file. All right, so what is the address of the .text section? Well, the .text section, that's where your instructions are. And remember, we said the first byte of the .text section should be the same as the address of the first instruction, because that's the first thing in that section. So let's come back over here now. Let's remind ourselves what our program actually looked like. So here's our program. We define section text. This global underscore start, that doesn't create anything that gets stored as data. That's defining, or that's just telling the assembler that start needs to be, the symbol start needs to be visible to the linker. That's all that does, but it doesn't actually create anything that gets copied into the section. The first actual thing in the section will be the first instruction, which we see appearing here right after the symbol start. Okay, so start is going to be the address of this first instruction, which is also going to be the address of the first byte in section text. Okay? Now, if we come over here and we're looking at the header, and well, we need to see what part of the section header we want to look at now. So let's go back to that. We want OC, that's 12 bytes in, and 10, 16 bytes in. That's what we're looking at. I think maybe what I have selected there is off a little bit, but we'll double check. So if we start here and we go 4, 8, 12, nope, it's exactly right. So starting right here, that's 12 bytes in to the .text section header, okay? And what did it say that would be? It said that would be the address of the start of that section. We also said that that address, and notice that because I have this highlighted, it's also highlighting copies of that elsewhere in the file. You notice that this address appears several places in the file. The important one that we looked at already was where it shows up here, telling us where the first instruction of the program will be, right? That's the entry point of the program, which is the same as the first byte of the .text section, okay? And then the other thing we wanted to look at is the offset. So the offset here tells us where the .text section starts in the file, okay? So the offset is the next set of 4 bytes, and there we see that's just 800000, but you have to turn that around, little endian, so that's really 00000080 as a hexadecimal number. So that's this offset right here. So right there, that is the first instruction. Those 5 bytes right there, starting with BA, that is the first instruction in the program. So now I've kind of detailed this out in the notes, and I might flesh it out a little further. So we look at offset 0x18 in the file, and we see that we have these bytes, which gives us the address where the first instruction is going to be loaded into memory. All right. Now we also looked at the section header. So let me add into the notes here. So looking at the section header, let me say if we find and look at the section header, then we can see ... this stuff. So this up here is also the address of the first byte of the .text section in memory. So you kind of, to see how we found that section header, I just had to kind of know because I sorted it out. Because I already knew that it would have this address, that's how I figured out which one was the correct section header. But I'm just kind of wanting you to get a feel for how this works. And so just follow along with the way I did it. If you need to go back and kind of rewatch that section of the video to understand that, go ahead. Basically, remember, each section header was 40 bytes, so I started from the end and I worked my way back in 40s. And I was looking for the section that already contained this combination of codes. And to find that, I could even have put that in this search here, 80800408. And then you have to put the cursor at the beginning of the file or it won't find them there. So we can get everything, all 4 occurrences in the file. Don't worry about why it shows up a couple more times. We're not going to get into that much detail about this file format. But having found that here, then we also find the offset here of where that section starts in the file. And that section and that offset is right here. And so there we see the first instruction in the file. And that's where, so when this file gets loaded into memory, this data starting here is what's going to get copied into the .text section in memory. And we can actually see the .data section as well. I think that comes after, so we figured out that this was that's our header for the text section. And then the next 40 bytes actually turns out to be the header for the data section. Don't worry about how I know this. It's something I had to take some time to piece together. So I'm not really worried that you can exactly reproduce this. But actually there are some things you can do that I'm going to show you that would help you reproduce this yourself. So again, if we look 12 bytes into this, we find these 4 bytes. So that's going to be the address of the data section of your program. And A4 is the address of where it starts in the file. And remember that in your data section, the first byte of data is the W, right? Maybe I'll add comments in here. So 87 is W, 104 is lowercase h, just to keep that in mind, and OXOA is new line like /n in C. Okay, so we're looking at that W from what's up doc, and that's the first byte of our data section, or I'm sorry, it's what's down doc. So let's click that, and we see that right here, that's this position right here, and we could just count up from A0, so A0, A1, A2, A3, A4, or we can look down here and see where it's showing us the offset down at the bottom, A4. So that is that W, that's the first byte of the data section. And so again, here we were looking at, here is where it gives us that offset from the section header from the ELF file. So again, going back to the ELF file format, we're looking at the offset now of the data section, all right, from that section header. And that's right there. That's that A4, and A4 is exactly the offset of this W, which is the first byte of data in our data section. Got it? If you don't got it, go back and rewatch. It's really step by step if you're careful. It's not that hard to follow, and you can see what's going on. Okay, so now that clarifies kind of what we looked at, a lot of what we looked at last week. And I want to do a little bit more with this video. So now let's just talk about that first instruction. So the first instruction of the program is move EDX message len, okay? And that turns into these bytes right here, BA12000000. Again, if we go back to our Bless editor, well, then we can look at these 5 bytes right here. Okay, now that's BA12000000. How does this relate to our command up here? Well, I've added a bunch of comments here, and as I've said before, when you're following me, do recreate these comments. Just go ahead. Take some time. Type them in. You'll remember things better. Get a screenshot showing that you did this and you created the comments, okay? Because I kind of explain how this relates to the actual machine code instruction as well, but we now have it kind of explained here in the notes a little bit more in a little different way. So it's these 5 bytes are that first instruction. The opcode of the instruction is just BA. Okay? The operand, it has one operand of the instruction, and that's just the number 18 if we interpret it as a decimal number, and it's 0x12 in hexadecimal, so that's why you see that 12 there, all right? But it's a 4-byte number. We have 12000000. But remember, little endian coding, little endian byte order, okay? So this is really the hex number 00000012. And that's just 1 times 16 plus 2 is 18. Again, why is it 18? Let's go back and see where that number actually comes from in our program. So we come back here. So that number comes from the symbol message length. Okay, so there's where it comes from. So message len becomes 18. Why is message length 18? Message length is 18 because we said message length equals this calculation right here. This calculation says take the current byte position minus this address. Okay, so take the address where the next byte of data in the program will be, or would be if there was another byte, and subtract this address from that. Well, wherever message ends up, wherever this first byte ends up in memory, that's the value of message. Okay, and so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 18 bytes represented in this list of bytes. So the next byte would be one more than that. And so if we take the difference between that and message, we get 18. That's where the 18 comes from. And boom. That's where we get 18 there. Or in hexadecimal, 1, 2. Okay? I wonder, what should we call 1, 2 in hex? Maybe 12s? I like 12s. Kind of like 12, but it's actually 18. But that's like 2 plus, the hex. So, maybe 1, 9 in hex. Call it I don't know, 9 hex instead of teen, because teen comes from 10. That's where your 13, 14 and everything comes from. So maybe we should call these things 9 hex, 3 hex or thir hex. Or maybe tex would sound better. 9 tex. I don't know. I'm kind of rambling here. At any rate, so it's something to think about. What should we, if we want to actually start working with hexadecimal numbers and talking about it, maybe we can call this twelx or twelix. Actually, I kind of like twelix. How's that? Twelix for 1, 2. And so maybe 1, 1 should be 11x. And so forth. I don't know. But something to think about. How should we name those things? Anyway, so now we know where that 18 for message len comes from. And of course it becomes 1, 2 in hexadecimal. And so we see in this instruction, BA encodes all the other information. BA tells us where we're moving from. We're getting data from immediately in the instruction, the next 4 bytes of the program. So BA tells us that. BA tells us that the number of bytes. It's telling us that we want a 4-byte number, not a 2-byte number or a 1-byte number. It's telling us where to move it into the register called EDX. So that's, BA is basically telling us everything that this instruction does. And again, remember, as we looked at it before, there's even though all the first 4 instructions are all that move command, each one has a different opcode because it's going to a different register. Whoops. So move EDX. So we're going to a different register each time, so we end up with a different opcode. And we could have other different opcodes depending on the size of data and where we get the data from. So the opcode tells us everything. We're copying data. It tells us the size of data that we're copying. It tells us where we're copying it from, and it tells us where we're copying it to. Or at least it tells us how to figure out where it's coming from. And it tells us where to copy it to, such as to a register. And so you're going to have, depending on these 4 things, you're going to have a different opcode result. But again, the nice thing with any language other than working with machine language directly is that you can usually forget about the opcodes, but I do want you to understand where the opcode, that you are getting opcodes and operands that go into your program, and that you just need to have a basic understanding of the relationship between your assembly language commands and what actually happens with the machine language. Okay, but you don't have to memorize the opcodes for things or anything like that. Okay, so hopefully that kind of is a rehash of week 2 video 1, but it dives deeper. The last thing I want to show you then is this readelf command, which is actually another way of getting a lot of this information out and maybe making it a little easier than to find things in the program. So this is a little bit of my little cheat that helped me out with this and helped me find where everything was in the program so that I could show it to you and act like, oh, I know what's going on perfectly, right? So I want you to try out this readelf command on your executable file. It's readelf. Use the -a option just to get all the information that it can produce. And then let's just talk about some of what it's showing you. So if you do readelf -a and then the name of your executable file, first of all, you get these magic numbers. And let's not worry about what those mean. They're magic, I guess. And these are numbers that will just show up basically at the beginning of the header. I think if you look at it in Bless, let's see, is that starting from the first byte? Yep. The magic numbers start right from the first byte. Okay. But they're not anything we have to worry about, really. Now, here is the entry point. So if you didn't have an idea what to look for the entry point, you could just do the readelf command and boom, there it gives it to you. So right there, if I turn these around for little endian in the reverse order, I can look for that in the file instead of actually knowing where it is, for example. Here it's showing you the address of the different sections. So the 2 that we're most interested in are the ones that we create as assembly language programmers. Here are the addresses of these 2 sections. And notice that inside the data file, inside the executable file, the offsets for those are also given. So again, you could go into the file and you could look for this data. Again, you have to reverse it for endian orderness. Also, it's only showing us 6 hex digits, but these are really 8 hex digits long. It's just that the other digits are always 0, so it's just cutting off some extra zeros at the beginning. And you're even getting the size of those sections, so that's kind of handy. Usually these would be bigger with a more substantial program, but you get the idea. So if you didn't know what you were looking for, now you do. So that's basically how I could come over here, and since I know from the format that each section is 40 bytes, I can count back, and then I'm looking for, this A4 or the 08, 04, 90, A4, or I'm looking for this stuff here. So I knew what to look for, okay, because I could come over here and run the readelf command. All right. So as you are working further in this class, now you have the readelf command at your disposal as one way to get some information so that you can better understand what's going with your files. So I encourage you to create, as you learn more assembly language, just create some random, some other assembly language programs and just mess around with the readelf command and look at them in a hex editor like bless, and just try and find where does your program start, where are the section headers, where's the program header, where does your .text section start, where does your .data section start, and so forth. Now, one thing I will say is it doesn't have to be true that your text section starts with the first instruction. You could put data in your text section. It would be kind of silly, but you could do that. So it's kind of typical for the first instruction to start with the first byte of the text section, but that depends on you. That depends on the programmer who created the assembly language file before it was assembled, how that ends up lining up. All right, so that is going to wrap up this video. Hopefully it's not too hugely long. I think it ended up running long, but I think this time through, we went through it in enough detail that you're sure to get it. And so I want to add that last thing. My cheat, all right, is using the readelf command to get info out of the elf format executable file, i.e. section addresses, offsets, and so forth, which is why I actually knew what I was looking for. So let me go ahead and say that syntax there, readelf -a, your executable file name here. All right. So that's the readelf command, and I'm going to do this and make it green. All right. And bold. All right, there. So that's the last tidbit for this video, and so until the next video, and hopefully I'll be able to get out at least one a day for several days in a row, and we'll finally have the videos lining up with what week we're in at the beginning of the week instead of towards the end of the week. All right, so until next time, I'm out.